I'm Cody Apple. I'm the Senior Machine Solutions Researcher here on site. And
I'm Trent, Lamont. I'm an additive solutions researcher.
and we're going to talk to you about machining some of these additively named parts. We'll start off a little bit about myself. I'm a Senior Manufacturing Solutions Researcher here on site. I've been machining for about 15 years straight. All of my work that I've been performing today has been industry taught. I basically have taken everything I learned from high school and developed it to program and operate huge scale machine platforms, to designing and developing new cutting tools for new applications, and creating new methods of manufacturing for aerospace components for building them out of its subsidiary, in its derivative companies. I'd like to thank the industry for collaborating with us. There's quite a few stakeholders in this project, or this realm of projects. So we got Mitsubishi Materials, Kennametal, and OSG supplying cutting tools for us to test and gather wear data on. We have, for machine equipment, we have the Geckertech, ARC 605, EN Solutions now, previously Doosan, PDF 5000. We've got our Renishaw AM, Ren AM 500. And we were using Mastercam currently on these parts. And I'd like to say big thanks to Angsters, who couldn't be here for the symposium, but supplied us with all our coolant and lubricants for metal cutting. And then we use the scan box, which is now Zeiss, to scan all of our stock materials. So the scope, it's four-pronged. So what we really want to do is focus on a quick turnaround of design parts. I know not all of you can see these parts in front of you, but these kind of represent a facsimile of different features that you'd find in structural applications. And these were actually turned around fairly quick. Once we had the process set up, we could actually change things around fairly effectively, and then print different designs, and be able to adjust on the fly almost. The second one is identifying issues that arise from print to machine. So the second you take one of these pieces and throw it on a CNC machine, you get a little bit of inconsistency, and we're going to identify some of those things that happen between print to machining directly. The whole point of printing these parts is reducing waste, and then using less of your cutting tools. Find that we're taking these parts down from billet, and we're using a lot of cutting tools, a lot of inserts, a lot of time. So we want to reduce a lot of that as much as possible. And then we want to identify, are these usable parts when they're all said and done? Can they have similar metallurgical, or at least low porosity, and heat treated enough to be used in application, structural application of any sort? So we'll get into our milestones and challenges. So we'll tap on the fast turnaround of the new design parts. So these are all steps that you want to take to kind of push a part through from a turnaround standpoint. So you want to focus, our focus specifically on structural component features. So we've got our, we've got pockets, ribs, walls, holes, bores, and floors, right? Everything that has to do with, structure. What we want to do is push the limits of our print volumes. So as you can see from these parts up here, it's a very large laser bed powder fusion part. So it's pretty much using the entire build volume and height. And then again, we're doing about similar sized parts across the board between two different disciplines. And these parts are actually made to fit perfectly within our DBF, our Doosan DBF 500. And so you want to design these parts for manufacturing, right? So as printed, you can kind of print any radius, any feature the way you should see it in a CAD design, right? But when you're designing things for manufacturing, you want to create radii that are compatible with standard cutting tools on the market. So let's say you have a corner radius in a pocket that's a 1/4 inch. You don't want to use a 1/4-inch tool to cut that radius. You'll get chatter, like we've heard in previous presentations. So you want to design a part with like a 260 or 275 radius in order to drive these cutting tools more effectively through the geometry. So just matching the design to what's out in the market right now for acquiring cutting tools is very important for design for manufacturing in general, not just for cut. Develop fixturing. So as you can tell, parts printed on a plate, you always get warpage, there's always heat, especially in these two processes. So finding a way to get uniform, machined accurate locating surfaces is of the utmost importance, because that's how you can actually set your whole product line up and revise and revise and revise, and literally just put the part back into the machine, hit go, and you're ready to run another part. And we do that repeatedly over and over with these parts. And then creating accurate stock models. You want to, especially in wire arc additive manufacturing, you want to make sure that all of your weldment is represented. So your CAM software has can use its full potential in keeping consistent radial engagements, axial engagements, and know when there's large globular forms in your stock. And it's very, very good at doing that. A lot of CAM software folks out there have this capability, but a lot of people don't scan in an entire weldment to use it. So it's very cool, and we'll see that picture of it down the presentation a little bit. And then, and I touched on optimizing tool path strategies because of your stock model. And then all of this can't get done unless you pick the right tool for the right material. So, titanium, Inconel, aluminum, 3 different subsets of tooling. If you don't pick the right one, nothing up above will work correctly. And I'll have Trent talk about the 2 processes.
Yeah, we're just going to provide a quick kind of 5,000-foot view of our additive processes used here, so we're all operating kind of on similar footing. Laser powder bed fusion, by far one of the most popular additive technologies for metals. I would say likely any metal additive parts you see today that are in use are high frequency LPBF prints. And it's really characterized by super high accuracy prints that what you're putting in is really what you're getting out. There is warpage, heat does affect things, but kind of what we put into our machine here up front is what we got out, as opposed to other processes where you can be close. And so we'll go to the next slide. And really kind of high level pros and cons here as well. It's high resolution, we have highly controlled build volumes, we have high reliability, infrequent consumable replacement, and minimal training. We can get our interns here at OMIC running our LPBF machines very quickly, as opposed to maybe some other additive equipment where the kind of training level required is much higher. But the build rates are low, and it's difficult to swap materials. And so all of these parts are of similar size, but the time it takes to build a part in LPBF compared to kind of other processes can be orders of magnitude high. And so in comes the other process. This is wire arc additive manufacturing. Dr. Saber yesterday spoke about our efforts in copper and stainless steel printing. Here we were doing single material builds. We use standard MIG welding equipment to perform this process that is attached to a 5-axis CNC gantry. This allows kind of users of standard CAM applications to come into these machines and use them more effectively. It's offered in CNC and robotic platforms. If you're really picking what flavor you want here, it's a very adaptable technology. We're typically using very high quality welders for this process that can put out a lot of heat and a lot of material very quickly. And compared to, say, laser powder bed fusion, where our weld bead, for our case, is 80 microns in size, our weld beads for WAM are 5 to 7 millimeters. So the amount of material we lay down at a time is also much higher. And so kind of with that, our cons, we have pros and cons. We have very high deposition rates, we have large build volumes, and we're capable of multi-material builds kind of with more ease. And cons though, we have low resolution. The amount of training required to operate one of these machines is much higher. Kind of CAM knowledge, especially 5-axis CAM knowledge, is limited. and frequent consumable replacements. During the course of printing one part in this process, depending on material, you could be changing out torch parts with a great frequency because they're just not designed for 100% duty cycle for 12 hours at a time.
And kind of getting into the parts themselves that we're using from a design standpoint. So you'll see 3 of these parts sitting up here at the front. After the presentation, we'll take a look at them. Both of these parts were made with WAM, so wire arc additive manufacturing. This was made out of 5000 series aluminum. This was our very first try at it. So this is grade 5 6AL 4B titanium. And then this part on the very right here is Inconel 718. Both of these parts were heat treated, so hipped heat treated, and then hipped aged and solution treated. So just like you would do with normal structural material, right? So we wanted to print and treat these materials as structures from a metallurgical standpoint or a heat treatment standpoint. And again, you can notice all of these features in these parts are conducive to structural materials, right? Or structural componentry. These are facsimile parts, like Hazard May said. This is a general project, so we want to just do a general swath of part features that could be familiar to your OEMs, people building complex structural assemblies. And then focusing the most on this part to the right, I'm going to hand it off to Trent, and he'll explain to you kind of the design behind it, why we printed this laser bed powder fusion part, tipped with its own support built into the print.
Yeah, so we have a lot of kind of options when it comes to design for additive manufacturing, and this is certainly not the furthest extent that you can go. A lot of vertically integrated teams will take the whole design of the part into consideration and build around the additive process. Here we were taking apart, and then we knew our end goal was machining, and so we tried to make Cody's life as easy as possible and our lives for printing as easy as possible. And so kind of the initial thing is we know we have so much Z height that we can use in our CNC machine. So we can't print over that, otherwise we can't machine it. And so we can't go full vertical and get rid of all support material. And so we have to kind of come down at an angle. And so we tilt this down. And so then we know, well, we need still a lot of support material up through the spine. And so instead of building very weak support material, we can also add in a stronger spine that we can machine off of. And so now we don't have to worry about as much vibration in our part at the end, because should we use kind of standard 3D printed supports, this part would start vibrating rather violently during machining, and instead now we can kind of make it much more stable. We knew we needed something to grab our part by after we removed it off the plate. We knew we wanted to print more parts on the plates we've gotten, and so to kind of speed that up, we can now build a block down here. We have something to grab by. It's easy to make a fixture to do that. We're just trying to optimize this process to make everybody's job easier in this. And so we've worked very well as like a collaborative team between machinist and additive person. And so we were designing the part to make everybody kind of have success. And also, of course, with every additive part, we were offsetting all of our surfaces. I believe for this component, we were doing an offset of approximately 1/8 of an inch. For this, we knew we only wanted to print so many parts, and so kind of going for high optimization on surface offsets could lead to machined parts without everything getting machined, and so we wanted to have a successful print.
Yeah, and the whole intent is to machine every single piece of this additive manufactured part, so we can really look at it as a fully machined part that hasn't been totally taken out of its work block with a lot of material. And this part's going to be taking an obscene amount of pressure from cutting tools, so we're going to probably be using the difference between carbide and ceramics to perform some of this Inconel work. So if anybody has experience with ceramic cutting, it's quite ridiculous and takes a lot of horsepower to be able to perform a lot of these cuts. So stability is a huge factor when it comes to machining these at speed, production rate speed. So the next one to get into is issues that arise from printing machining. We had a lot of them, and they were kind of fun to overcome. Not too many, but fun, nevertheless. So I'm going to focus on basically the wire arc additive parts, because they're the most kind of fidgety, because there's not really any uniform surfaces when it comes off the Deffer Tech. So print-to-print geometry consistency, you can kind of see right here, they are different. They're different, they're located in different spots in their plates. The The ribs can be slightly higher, slightly shorter. Your distance here where you're tabbing out your part to break it off. You have less clearance, more clearance, and then your plate thickness changes. So slamming that into a CNC machine and just probing it and hitting go is kind of out of the question, unless you have a nicely scanned part like we have here, and are able to machine in some datum surfaces as correlated to our printed datum surface that it's the most uniform piece we have from the print, which is this web down here. And that's how we held the plates to actually put these locating surfaces for a dovetail fixture on the bottom. So you have a flat surface, we're able to grip extremely strong and take some very heavy titanium cuts to the profile of this to more net. And then sometimes the base plate just moves so much that you have to remove the part like we are doing with these incoming plates, right? We don't want to machine these base plates down, half an inch just to flatten them out. We'd rather just wire medium the part off and then build a fixture based on the geometry we built into the print. And that geometry being built into the print can be more uniform based on a bunch of different part designs, right? So that's more ongoing research in itself. And then Trent's going to chat about how he got to making these parts so quickly on the wire arc additive machine.
Yeah, so in the WAM process, heat is the enemy. While printing kind of the central spines of these structures, it's often not a problem. You can just wait and then heat will dissipate and you can keep on printing. And we were laying down lots and lots of material very quickly, and so these parts got super hot. Depending on your material and your circumstances, we have a lot of challenges as well with printing on dirty welds and uneven surfaces that may have already warped. And so those are kind of difficult to overcome. We go to the next one here. And then also, you kind of intuitively think in your mind at first, well, I want to print this part, we'll print all one side, we'll print all the other. This is probably the most disastrous way to print one of these parts. They often will turn into a potato chip and you'll never get to side two. The more and more you print, the more and more it will warp. And so instead, we kind of take this approach that the 5-axis capabilities our machine offer, where we can print on one side and we can print on another, and we disperse the heat evenly. And you think, oh, this is intuitive, it's easy, you should always do that. But you have to mess up first and learn that that was not what you were supposed to do.
Yes, glorious.
So then, now we can print to an alternating strategy. And this allowed us to build our components much faster. We were laying down lots and lots of titanium. We're going through 45, 50 pounds of titanium wire in 10 hours.
Mm-hmm.
So we're cooking.
Exactly. And all of those center spine supports were actually very straight when we got to them. The only real change was really the build up from side to side and how tall the spine were. The straightness due to this came out almost perfect.
Yeah, the spine is the best kind of datum feature that we can provide out of these WAM parts for this particular kind of application. So creating as straight of a possible spine is kind of our biggest benefit. And so then this allowed us to be very predictable part to print, and without much distortion. Of course, we're going to have some just based off of the heat inputs that we're having. And by the end of testing, this part program was optimized down to 9 hours of printing and about 12 hours of total time in the machine. For reference, the LPBF part that we're printing currently, admittedly we have one laser on our machine, so it is slower than the standard industry machine, is at 56 hours for a similarly sized part. And so we're laying down a lot of material. But part of this is also, in this particular machine, under titanium, there's no operator interaction with your part for the entire process, or easy access to your welding torch. And so kind of the faster and more predictable you can get with, much like tooling, replacing your tooling right on time, replacing torch parts right on time reduces downtime during the printing process, and this number can just get lower and lower.
Yep. So it's outstanding amount of material being laid down inside. So now we'll talk a little bit about waste reduction and retention as it compares to your stock and your tool path and how it all kind of rolls in together. So printing tip as close to near net as possible is crucial, as you know. But you have to choose what is as close as you can get while still holding the part within your print, right? And that's including all of your heat treatment, your warpage, anything that could occur to the part post-print, right? You can get very close with laser powder bed fusion, but you're a little bit more off when you get into wire arc additive manufacturing. You can definitely see the difference in the layout of the material. And then that will enable you to use powerful tool paths referencing your stock model. So here we're just looking at a tool path based on a stock reference in my CAM software. And it is able to recognize the interior weldment beads, and it's kind of hard to see, it's pretty zoomed in, but it's literally just like wobbling around each individual weldment in order to keep a consistent radial engagement on the cutting tool. And then it's recognizing that this has a cavity here, so you're able to drop in tools where you would normally have to machine out entire pockets, waste entire cutting tool assemblies, and you'll have to just keep changing over and changing over. You go through twice the amount of tools by the time you're done with this part. And then using sustainable cutting materials. I know a lot of these still have to get strapped to tungsten carbide, but it's a step along the way. Using as many non-mined materials as possible, like polycrystalline diamond, cubic boron nitride, and ceramics, really. These are materials that are generally lab grown, and there's not huge lines behind it, right? And they're sustainable, can be recycled a little bit, and actually have very, very high performance ratings in these kind of materials. Speaking of cutting tools, just a small screenshot of some of my data collection on cutting the titanium piece you see up here. So it's kind of hard to see, but this top row these are individual tools running in their individual operations, each one running to the tune of about 30 to 35 minutes. You see a brand new tool, you see its tip, basically radial flank, and then you see up on the flute where the depth of cut notch would be in the tool path, and then down here you see it after it's been used. So we have seen across all of our toolings except our ball end mill that was doing all our coloring operations, we found it very difficult to find just even the depth of cut notch in these tools. They're meant to be used as heavy roughing tools for long periods of time, but if you take these heavy roughing tools for titanium and put them into an application where they don't have to cut as long, you can get exponential increases in tool life part to part. And therefore you can get edge retention like this, where it's extremely smooth, and then down here, all you see is the projector. Then down here, you see a barely used edge. You don't see any chipping, you don't see any edge buildup. These tools are designed to cut. And so what you're getting is just incremental great gains in part-to-part consistency from an edge standpoint, and you can set up your tools for part runs in the future. You just keep them in there. And this is just tungsten carbide. If you switch over to some of the more exotic materials, you need it to last a lot longer than these kind of cuts. And then resulting material condition. What do these parts look like when they're all done and machined? Can they be used? Can we apply them in our everyday assemblies? Can we actually transition to this kind of process moving forward? Especially from a design to product standpoint, first articles, things like that. So we use the HIP, so Quintus has been a very good partner with Trent to produce heat treatment cycles for all of these parts. We're able to run a lot of porosity out of these parts. I know laser bed powder fusion already doesn't have too much porosity in it, but wire arc additive does. And it's very prevalent in this piece specifically. The other ones I have out at CT scanning company now. So I wasn't able to have one here that was hipped. But hipping utilizes chamber pressure and heat. So it technically uses heat and pressure to squeeze porosity out of materials, similar to as you're pressing a forging, you're using heat, plastic deformation, and pressure to push all of that out. So I found it to be a similar process, but not exactly the same, but it would be suited for additive in this way because it's not to be as forged or as close to forged as you can get. And we want to measure all of these parts using industrial CT scanning. So we want to look inside of these pieces and see what kind of blades we squeezed out of them, right? And so we were working with the scanning company that we partnered with for this project. They were able to give us some very good feedback. So this is the titanium 6AL4D part hip and final machine. And so they're able to actually get down to about, 140 micron voxel size for a part of this density and size. Pretty difficult for industrial CTs to make that happen. A lot of CT scanning has a lot of noise in it, so you'll find these pieces here to be like anomalies, like these dark pieces. It's kind of like an X-ray tech. You gotta know what you're looking for and know what a void actually is. And so they were showing me an instance of a void. This one sitting here is, I want to say, it's about 6 thou. But this is the closest thing to a void they found in this part after hipping. When the part you see up here has, voids 8-inch. They're large. So we were able to squeeze a large amount of inconsistencies out of these parts, and you can tell that in machining. The non-hipped parts, you were cutting through, opening up voids, seeing carbon layers, and just getting a general, abrasiveness to your cutting tool that we did not see after hip treatment of these parts. And then,
So
talk a bit more about it.
Yeah, 3 of our 4 parts were run through an optimized hip process that was recommended by Quintus that they've seen kind of developing in the aerospace industry. This hip process is to maintain just a little bit of that microstructure that we can develop through additive manufacturing because it's very difficult to achieve otherwise, while taking out your porosity and still kind of homogenizing the structure.
Right.
And then after pre and post hip scans were taken to see what kind of distortion that we were witnessing, and we did not see any significant movement after hipping. So our parts were going in straight and coming out straight, which is nice.
And then some of the outcomes and applications of this. So rolling through, we were able to use structural components, part of our design motif. We were able to run three different structural alloys. We were able to use 2 different print strategies. We were significantly cutting time from cutting these out of just block, plate, what have you. We definitely reduced material. You look at a bucket of chips after hogging any of these out of billet, we barely used a quarter of a 55-gallon drum when machining any of these. So it's very, very economical from a material-based standpoint. Edge retention, we all know that if you get a good program, you get good cutting tools, and sometimes uneven surfaces, you actually get a lot of edge retention with today's cutting tools on the market. And then we were able to show through CT that the voids inside of the wire arc additive manufactured parts were significantly reduced, and that led to the consistency of machining and edge retention. So there was a lot of connections made during this entire process.
Then we just have some pictures here of our Inconel 718 part before it got aged. And so kind of post-hip, it was a light, nice marshmallow brown, and then after aging, it is now turned purple. Yeah. So we're, with kind of our hip, we do have Quintus's Purus capabilities, which drastically reduces oxygen pickup during the hipping process. And so like with our titanium, you see that it's nice and silver, and it's not orange, it's not purple. And so the same can be said with nickel alloys, but it does still just pick up a little bit.
Yeah. And then applications. They can include complete manufacturing, start to finish, of structural assemblies in very low volume, right? So your takt time being, in this instance, 9 hours. If you can match everything downstream to that, you can actually have a production flow of parts coming out every night surface if done correctly. And then you can also use some of these processes to do, rapid design and tests prior to getting forgings and castings, right? So you're, let's say you're designing a new part for your complex assembly, and the casting house and the forging house says it's going to take 8 months to 2 years to get you your dies. And that's a lot of time you're sitting there waiting for your design to basically get accepted, approved, and get your first casting and forging. You can actually take this process, print your near net forging with all of your locating surfaces, or your casting with laser-based powder fusion. Align all your fixtures, align all your cutting tools, get all your programs ready and set up, and then have to do minimal tweaking by the time your actual forged parts or your cast parts come in, and you're doing cyclical production runs. So it actually front loads your design and refinement. So then while the forging and casting house is building or in work and building your dies, you can give them design revisions as you experience them instead of as you talk about them and you say, does this work? Yes, no, okay, we all agree, let's send it to the casting house, and then, but in this instance, you can actually test it, use it, make sure it works, make sure this structural component actually fits into your assembly in real life, and then you can just work ahead to finalizing your design and be able to move forward in production, in development. And some of the next steps we want to do is to create parts, take other people's parts instead of these facsimile parts and actually redesign them for additive where there's material where there needs to be and not material where there doesn't. Because a lot of parts are designed from a manufacturing standpoint. We want to cut this out of a forging. We want to cut this out of a block. So we need to put all of these, thick, very geometrically straight shapes, around. But with scanning and printing, we want to be able to take it apart, redesign it, and then give it back to the customer and say, test this. Run it through your rigorous testing in order to see how it compares to your off-the-line production part. And that takes a partner. Right? It takes somebody to say, hey, I've got a part of that size. Why don't you design it to make it better and then feed it back? And I'll test and see if it's metallurgically strong. It's dense enough. It doesn't crack. It doesn't do all the things that I don't want the part to do. So setting up this process is kind of a baseline to what could possibly be for structures. And then another one would be taking these surfaces that don't technically need machined, like anything between joints, most bores, holes, connection pieces need machined, but if you want to, like let's say, shot peen this part or reduce residual stress on the surface from printing, use a process called CASF, so it uses water cavitation and a garnet to basically smooth the surface of the part and make it more like a pickled surface. But that will also de-stress the part significantly. And then the last piece, and that will also remove partially atomized powder that in that instance could kind of scrape off and get into your assembly. So you always want to eliminate that, especially in internal cooling passages. Make your internal cooling a little bit more laminar. And then the last one is developing a fixture that can hold all these. I really want to come up with, there's a lot of these designs out there using pins and various pneumatics. We really want to get to the state where Trent can say, hey, Cody, I need something machined. I'll just hop on my magic fixture for a subset of geometry and just go, all right, my work offset's here, my scan's loaded in, and I know exactly where this thing sits. And I just let the software move mountains for us and locate the part correctly and machine all the pieces that need to be machined. And that's it. Any questions?